want to acknowledge all this work's heavily relied on my colleague Radford Neal at the University of Toronto. And I've kind of bastardized the title just to put a few themes. You know, one of my own personal themes, which I guess is probably the theme of this whole meeting too, is model data integration. How can we do it more objectively? And this talk is really, in some sense, just showing a rough and dirty calibration of how to of a moderately expensive Earth systems model. So hopefully of use to other people as well. Giving some context in terms of sea level, since some of you don't have any paleo background. Here's a 20,000 year signature of the ice sheets in terms of global eustatic sea level, so it's a volumetric equivalent of sea level change for mean ocean level in meters relative to present day. This is 20,000 years in the past, actually only went to 8,000 years ago. And this record's based on Aquapora palmata. It's a coral that usually stays fairly close to the surface of the ocean. It was taken from Barbados region. Key features to look at, just I want you to note, is that ice volume changed at different rates. So there was fairly constant change. Well, actually there's no data, so there wasn't too much change from 18,000 to about 15,000. Then there was this very abrupt interval called meltwater pulse 1A, where given the error bars between 16 and 25 meters of global sea level change occurred within 600-700 years, possibly a lot shorter. Again, there's a data gap, so we don't know how fast it was. And then, again, more variability, bit more controversial meltwater pulse 1B around 11,000 years ago. And a bit more context too. Again, for some of you, this is probably old hat, but as modelers, I think it's important to have context why we're doing this stuff. I try to remind my students of that all the time. And so, one obvious reason is to build confidence in ice dynamical models, in the models as well as our understanding of the dynamics, and especially in order to predict, as Michael Gill mentioned yesterday, I guess what predictive understanding, predicting future sea level change, most difficult to do with issues about abrupt sea level change. Those of you who've read the IPCC know that the issue of the instability of Greenland and West Antarctica was left as an open question. And in terms of this instability, one issue looking at the past is what was the source of meltwater pulse 1A I just showed you, 15 to 25 meters of sea level within 500 years, a lot of ice. And a lot of sea level change would take out, I think even 2 meter sea level change would affect hundreds of millions of people. So if we're talking about larger sea level changes, we could have very large impacts on society. We also need to know past ice thickness changes in terms of deconvolving surface altimetry measurements to extract present day ice volume changes, because surface altimetry of the ice depends not only on ice volume but also on ongoing changes of the surface of the solid earth below it in response to past changes in glacial loading. And it's also, we need ice sheets for building confidence in our climate models, and again, improving understanding of past climate changes, not just ice dynamical changes. Ice sheets provide 3 important boundary conditions for paleoclimate models. I won't get into that. There's also more dollar or present day issues I've been involved with too, in terms of anything from mineral prospecting, groundwater, hydrology, long-term nuclear waste storage proposals, etc. And again, for you, this is more for the audience. Whoever anybody's looking at this videotape for here, probably it's not much of a point, but at least it's old hat. Uncertainty is unavoidable when dealing with the climate system, and I guess likely most environmental systems. And this uncertainty is very hard to quantify and to deal with because of the inherent nonlinearity in these systems. So what? This is a personal example. I work in Newfoundland, St. John's, Newfoundland, in Canada, the eastern tip of Canada. And this is a plot of total landings from the cod fisheries in Newfoundland, going from 1850 to year 2000. In tons, fish landings in tons. And around 1960s when we started scientific management of the fisheries, all based on linear response modeling of the stocks. And you can see what happened. And it still hasn't recovered. And when I talk to my colleagues on the biological side, they're pretty pessimistic about a recovery. There's been talk about ecological niches being taken over by jellyfish, and also just and it's not just been fish landings. There's also been questions about changing temperatures in the oceans affecting the ecosystem. Pardon?
In what sense do you mean the policy was?
Because the landings were controlled by. Well, that's how the quotas were set for the fisheries. Okay, so the old fisheries models were all based on linear response models, and that's how they set quotas for fish landings. So even though they would have been much more careful in setting those quotas, should have been a sustainable fishery. One thing that really struck, when I started at Newfoundland, one memory I had was around grade 5 geography class, or history class, and they were talking about the discovery of Canada and how you could barely paddle through the waters of Newfoundland because there was so much fish. You were just like trying to go through these schools of fish. And that was so an amazing resource, totally destroyed, because our policy experts work on a linear paradigm, even though the environmental systems are nonlinear. Okay, enough for politics. Outline, this is more of methodology talk, but I do want to focus a bit on data and on the physics as well. I think to calibrate any kind of model system, you have to understand the physical system as well as the data. And the goal of this project is to determine the probability distribution for deglacial ice thickness, surface topography, elevation, and meltwater discharge evolution, at least initially for the last 20,000 years during the deglacial interval. Given observational constraints, I want some consistency with climate, improving that as we can get better climate models. Right now, as I'll show you, I'm just using climate forcing, and internal consistency with glacial physics. In the past, the main ice sheet models used by paleoclimate modelers, for instance, for boundary conditions for the first two paleomodeling comparison projects, have been based on geophysical ice models, which are basically just conceptual Lego block models moved around by hand and then run through a forward sea level solver and compared to sea level data and then retuned by hand. No glacial physics in there, no error bars.
What is deglacial ice thickness? What does that mean to you?
It's a 3D history of geographic distribution, deglaciation.
It pertains to the period since the last glaciation.
Yeah, so it's 20,000 years to present.
That's what you mean by that phrase.
Yeah.
That's okay.
Okay, no, bring those questions up. I always make assumptions who I'm talking to. And a longer term goal of my work is to develop a joint probability distribution for ice and climate over the whole glacial cycle, last 120,000 years. In terms of the physical system, here's a cartoon of it. Key components from ice sheet perspective. Some questions about the flow law, but I think those are more, except in fast flow regimes, those are generally a secondary concern. But anyway, you basically have material that's deforming under certain rheology. That deformation depends on the temperature profile through the material, depends on the stress field, and basal stress conditions, depends on the geometry of the basal boundary, and depends on the surface mass balance, accumulation and destruction of surface ice, and also at the margins, at the marine margins. In terms of challenging processes, temperature field in here, that's pretty standard thermodynamic modeling, that's easy. The ice dynamical modeling, when you're away from fast flow regimes, is pretty well represented. I use the shallow ice approximation, it's pretty standard. Basically treats the ice as, some ways you can think of it as thick molasses. It's a just a viscous material with nonlinear rheology. And but that approximation somewhat becomes pretty inaccurate where we have fast flow, and over time I'll be improving the physics in the fast flow areas. It also becomes quite inaccurate where we have ice shelves where the ice floats. And especially determining that transition point, the grounding line where the ice goes to flotation, has been a major issue among the community in terms of coming up with accurate models to predict the dynamical evolution of that grounding line. Another major uncertainty is we don't have a physical calving law appropriate for large-scale models in the community, nor do we have decent basal hydrology models. Again, it's partly a scale issue. We can run these continental scale models. I work on the order of 25 to 50 kilometer scale grid cells. Basal hydrology processes work on tunnels that are on the order of tens of meters, 10 meters. So we have, again, just like in other climate fields, we have a scale problem here. The basal stress also depends on the surface material. We can somewhat model that, and that material can also deform, and that we think is a major component of fast flow processes. The geometry changes due to bedrock deformation from the loading. So again, and it's a viscous response, so you push it down, it takes a while to deform. When you remove the ice, it takes a while to spring back. And we're still under, as I'll show you, we're still under basically returning spring back from the last ice age. But the biggest unknowns are the climate forcing. Even if we could run a GCM over the last 120,000 years, we'd still have major uncertainties in surface temperature, which controls ablation, and especially in terms of surface accumulation. Okay, so that's the physical system. In terms of the modeled system, as I said, we're using a standard shallow ice approximation. For those in the climate field, it's equivalent to shallow water equations, so it's vertically integrated approximation, but with 3D thermodynamics. Viscoplastic till deformation, the bedrock rheology uses a Green's function approach, so it's global response to surface loading, and number of heuristic, but I think fairly well-grounded parameterizations given the state of the art for calving, surface ablation, computing snow fractions. The main thing I want to emphasize with what I call glacial systems models, unlike a lot of ice sheet models, I put a lot of work into diagnostics. So I can run isotope tracers through the ice. I calculate surface drainage, which is actually dynamically coupled with the ice, so I can have lakes forming, which also can cause calving on terrestrial boundaries of the ice. And I have a relative sea level solver, which computes the measured sea level response. I'll show you a plot in a minute at the margins of the ice in marine environments. And again, and that's a non-trivial calculation because you have to take into account not both the deformation of the Earth, change in the geoid, gravitational potential is modified from the mass of the ice sheets. And that's a significant enough effect. Changes in global and global ice volume affecting global amount of water in the oceans. But then as modelers, we always have to remember that there's a big difference between what we're modeling, our actual models, and what we're actually trying to model. It's good to keep that in mind. I've tabulated some of, I've already kind of stated most of these, just maybe a few points to iterate. The biggest uncertainties in the model are the climate forcing. Next, I would say the calving law, and as well as missing components in terms of englacial basal hydrology, where the meltwater, subglacial meltwater goes, and as that water percolates through the base of the ice and pressurize the base and basically kind of float the ice and allow is critical for fast flow processes. Sediment transport can change the basal stresses and also affect fast flow processes. The isostatic adjustment of the bedrock, again the change in the bedrock geometry due to the change in surface load, is one component. I've got a fairly state-of-the-art model, but I have no error bars on the rheology used for the Earth. So there's another major uncertainty that I can't even quantify because nobody's given me any kind of error bars for the rheology of of the Earth models. And an ongoing question, which I'm trying to keep on bugging Michael here about, is how to better account for structural errors aside from adding parameters in the calibration. So given the climate issue, it's critical for the model evolution. You know, can't run a GCM. What I use is last glacial maximum precipitation, evaporation, and temperature climatologies from the PMIP Paleomodern Comparison Project. So this was international project comparing model runs from international climate modeling centers, and I took the mean and the top two EOF fields, empirical orthogonal functions, of the intermodal variance. Okay, so I'm trying to capture the variation in differences between the model, but I've also restricted to the top 6 GCM, high resolution GCM runs.
Is that PMIP2?
These are PMIP2, yeah. And then I also use, so that gives me a last glacial maximum climatology, and then I use present day observed fields and separate analysis for present day. And big issues then is how do you get from, you know, glacial state, you know, defined by my LG, last glacial maximum climatology, to present day. And what I use is the basically glacial index defined from the GRIP ice core record from the summit of Greenland, which goes back 120, actually goes back farther, but I take it back 220,000 years, and I've just weighted it as interpolating function between last glacial maximum, or 20,000 years, and present. Now, given the crudeness, especially the climate component, I'm trying to perhaps adjust for that by adding a lot of model parameters in the calibration, and that's been evolving over time. So the first column is the amount I'm using right now for Eurasia. Second column is how much I used to use for, and that wasn't even the original, but until about a year ago, how much I was using for North America and how much I'm now using for North America. Okay, so ice dynamical parameters in terms of fast flow response, 3 to 5. Largest source of uncertainty in my mind is regional precipitation. So I have 14 to 19 parameters controlling regional response, precipitation and regional response, surface elevation changes, and surface temperature. Ice calving, I said, is major uncertainty, so you have 4 parameters with that. I only have 4 with temperature, and I'll get into the ice margins in a minute. And what this adds up to then was right now 29 for Eurasia, 39 for North America. Started out with 23 for North America. One of the biggest challenges has been, as I calibrate and get given more data, unable to fit the observations, so for different reasons end up having to add more calibration parameters and restart the whole process. Okay, so that's the model. In terms of the observational constraints, and again, any kind of calibration is important to understand what the data is, so you can understand the uncertainties. One key source of data is relative sea level changes, and those are usually basically, in terms of the actual data, it's could be driftwood, but the most common is mollusks, you know, basically clamshells embedded in raised beaches or kind of slumping cliffs. So here's an example of raised beaches from Hudson Bay. And we also have beaches in non-marine environments. You can see wave-cut edges called strand lines. So as the ice sheets formed and depressed the terrestrial land and then receded, they created, again, a depression that took a while to spring back. And in that depression, lakes formed. They're called proglacial lakes. And those lakes stayed at certain levels for a while and created wave-cut beaches. And you go across, for instance, Manitoba, you can see extensive linear forms that we understand were these long beaches from way back where there was a very large lake. Another important constraint, because these constraints are only available where there was large lakes or marine environments. And for other regions, looking at present day rates of uplift inferred from either long-range baseline radar interferometry or repeat GPS measurements. Here's tabulation of all the relative sea level sites we have for North America. And here's an example of what the model predicts as well as observations for 2 data sites. So this is Hudson Bay, southeast Hudson Bay, and this is Mackenzie Delta up here. And key points I want to get across is this data is quite noisy. Some of it's one way, so some of these mollusk shells can live anywhere from 20 to 100 meters below the surface of the water when they were alive, right? So they're only giving you really a lower bound. Some mollusk shells are intertidal, so they're hopefully staying within 5 to 10 meters of the water. Sometimes they might get displaced by seagulls and that. So and you have to, hope that whoever's been collecting these samples is taking account that when they're found, they're embedded in a living position in the earth. They haven't been moved around. So anyway, there's quite a few uncertainties with those samples. If it's driftwood sample, then it gives an upper bound. Driftwood generally stays roughly at the margin of the water, or it can get pushed up by waves. So it gives you a pretty close estimate, but slightly with error bars projecting downwards. There's other types of data, including archaeological sites, where again they would be an upper bound. People were living somewhere above the water, but we generally think native populations were living fairly close to the water in these kind of settlements where these data points were taken. So you can see the scatter in the data, and what we look for then is an envelope that matches the error, the directions of the error bounds.
What, just to confirm, the raw data here are large number of samples of things, and what you have is the height. I mean, you have the current level in some sense of that.
Yeah. So we have present day elevation of that sample, and it's dated usually by C14 carbon dating. Some samples, your age, there's actually a lot of dates from OSL, optically stimulated luminescence, which is okay. So it's basically elevation point at a certain time. Uncertainties with both the dating and with the elevation, right? So I should have mentioned this is present day surface. This is elevation relative to present day mean sea level, and this is time going 21,000 years in the past to present. So you can see, and these are 4 different model runs, okay? Just give you a sense of the kind of response you can get for projected relative sea level. Now what happens here, the data ends here because at this point the ice was covering that region, okay? So, but the model, when I do the calculation for relative sea level, it's done post-processing, it calculates as if the water could penetrate through the ice. So it's still calculating loading and geoidal perturbations, but it's giving you a sense of what the sea level would look like if the water could go right straight through the ice through time. But even though there was in the past 21,000 years ago, sea level was about 120 meters below present day. Sea level at the margins of these ice sheets was well above present day. Here it was about 200 meters above present day, just because the Earth was pushed down so much from the regional loading of the ice. Make some sense? Okay.
So you've got the data elevations and dates. Some of the things, depending on what they are, they give you upper bounds or perhaps lower bounds. But one of the big issues here is the Earth compression.
Yeah.
So in your, I mean, the amount of bounce in terms of the samples that you're talking about across that particular part of Northern America, the Earth compression is of the order of several meters, but sometimes or several tens of centimeters or what?
Oh, the dominant signal here is from the Earth compression.
Okay.
Basically, it's under equilibrium. It would be basically just flotation. So it's the ratio of densities of the ice to the water. So if there was last glacial maximum, we had here about 3 kilometers of ice. So the depression would have been about 800 meters.
Okay.
Okay. If under equilibrium conditions, there's pretty long time constants, so it probably wouldn't quite reach that, but on the order of that amount.
It's like Scandinavia is still rising.
Yeah.
But
Many millimeters per year past
in terms of
How much, what did you hit? Meters per year, millimeters per year?
I'll show you a plot of that actually.
Falling, the Baltic, it's the land
Yeah.
Baltic.
That's the rate of,
Okay, I'll jump ahead since you brought that up.
okay,
Here's the ensemble calibrated model of present-day uplift for Fennoscandia. Okay, so this is in millimeters per year. You can read this. This is 12. The end of the green is 6 millimeters per year.
So that's
that's a meter per century.
It's outpacing sea level rise.
But that's the order of a meter per century we're talking about, is that right?
Yep.
Yeah.
In the peak areas here. And again, here there's no data, so for this is all submarine, but this is just from the model. There is data here, and this is again part of the calibration data set. Okay, so that we're there. I just want to finish. So I have a lot of data points, especially for North America, but a lot of it's noisy, and there's also large variation in data density. So one thing I do is I reduce the sites. I've kind of gone through by hand based on guidance from the experts in the field in terms of which sites were better, and did some data thinning. So the actual calibration is done with a reduced set of data sites, and actually a reduced set of data points, because you can see there's a lot of correlation. You know, most of this data is pretty useless. There's no point in trying to calibrate against all this data down here. So basically I'm trying to calibrate against key data points that constrain the envelope of possible trajectories. Yeah.
Steph, on exactly that subject, the work I'm doing at the moment with Mark Siddle on sea level rise, we had the same problem, which is correlated data sets and non-symmetric error bars. And rather than thin, what we decided to do was to aggregate into blocks by time and space that were large relative to what we thought was the correlation length of the process. And the reason for doing that was partly because that was a simple way to include all the data, but also because you can then use a central limit theorem to get around the problem of one-sided and asymmetric error bars. Because within the block, the averaging process makes the mean of the block more Gaussian. And it's a very natural way to induce a likelihood function when the underlying processes themselves are not at all Gaussian.
Does that work? I'm just curious.
Yeah. Well, you have to take quite big blocks.
So how big were these blocks?
I think we were looking at blocks of either 1,000 or 5,000 years over the last.
Oh, so temporal blocks you're talking about.
These were temporal blocks. Yeah.
So you averaged over. But it's a non-linear. I'll have to go through this because it doesn't really make sense to average the data points over time because the response is changing over time.
Well, we wouldn't have liked to have done that either, but otherwise we were going to really struggle with the describing the likelihood function because of these one-sided error bars. Yeah. So what we did is we fitted a triangular distribution to every error, effectively, changed that into a standard deviation, and then used a central limit theorem within the blocks to approximate the likelihood function with the Gaussian.
Okay, I'm going to have to sit down with you afterwards to discuss more than exact error models on this. That sounds interesting, but
There's a
I'm not gonna
special
get my head around it right now. But anyway, yeah, so that's, as Johnny pointed out, error models are a challenge. So I did this anyway, data thinning based on kind of inverse data density. Well, and also did weighting then too. So I thinned and then I weighted each of the sites, partly based on the types of data in there, as well as the data density. So, you know, this site, there's only one site for this whole region, so it gets a lot of weight. Lots of data up here, so each one has very little weight. Same thing for Eurasia, just give you a sense again where the data points are. And I already showed you this. So for, I also did data point thinning for uplift. So for both North America and Eurasia, I have about 6 or 7 data sites that I'm using in the calibration. In the Markov chain sample anyway. I use a full set of data in final scoring of ensembles, I'll get to in a minute. In terms of constraining deglacial history, the relative sea level response is in some ways a time integral of ice load and margin position. So if we really want to constrain the ice, both the position, the actual ice load and position, we need another constraint. And so I've been working closely with glacial geologists in the field to get margin chronologies, and This is North American ice margin chronology created by Art Dyke, who is basically the world expert on Laurentide deglaciation. Consists of 36 time slices, but he was not able to assign error bars. It's an ongoing project is trying to come up with a new margin chronology that includes error bars on these isochrone positions. Originally what I did was allowed about basically one plus or minus one grid point uncertainty for these error bars. But in some ways that's really bad, because what happens, there's differential rates of retreat, as you can see here, for instance, compared to here. There's also varying degrees of uncertainty. Down here there's lots of data. It's accessible. You can walk around and see these geological landforms that were dated and used to infer margin positions. Up here, this is very inaccessible. No roads, helicopter travel. So there was a lot of judicious guessing and conceptual interpolation done by Art in these regions. But that's not. I don't have any actual way of quantifying those uncertainties right now. What I have done to take into account differential temporal rates is now I use a plus or minus one time slice uncertainty. So every time slice, I allow that the actual ice was somewhere between that margin position and the previous time slice and the next time slice. And one other key kind of subtle point is that the complexities of this chronology are never going to be captured by a single ice sheet model driven by even a state-of-the-art climate model. There's too many high-resolution processes going on. So what I do then is I basically have a nudging component in the surface mass bounds that gently forces the ice margins to stay within these error bars. Okay, so if it's within a time slice right now, plus or minus one time slice of the target margin, then I don't do any nudging. If it's beyond that, then a nudging is imposed, so the surface mass balance is adjusted somewhat. And again, I put ranges on how much adjustment I allow based on my judgment of what would have been regional variations in climate and surface stresses. And then I keep track of how much nudging's been done in terms of how many grid cells had to be nudged. And I use, as I get into a minute, I use those. I have a cost penalty, so I do this nudging, but then I also penalize calibration for the amount of nudging. More nudging, the worse the run. So I'm trying to find basically deglacial history that's has climate forcing as much as possible in consistency with the ice evolution. Okay, but still trying to maintain the inferred ice sheet margins. And within this process and the nudging, I have 2 to 6 ensemble parameters, depending which continent I'm working on and when I started. The Eurasian chronology is a lot nicer. It was created by colleagues in Bergen. They have kind of the dated project where they created a GIS database, and they created 1,000-year time slices for the ice margin position, as well as max and min chronologies as well. So for that, I do have meaningful error bars. And again, always remember, data, model, reality. There's big jumps in terms of the scales. The modeling is done on 25 to 50 kilometer grids. This distance from here to here was about 1 kilometer. And a lot of detail there. In terms of summarizing the data, key thing, I don't worry about the details, but some of the data is basically large geographic constraints. They're kind of integrating large-scale features, for instance, the amount of margin forcing required. Some of them the data is geographically local but temporally integrative, for instance, relative to sea level and present-day rates of uplift. They depend on the recent history or the past history of surface loading. And there's also some constraints which I wasn't able to come up with a good emulator for. They were too dependent on details of local ice margin position. One is marine limits, basically the maximum amount of recorded marine inundation, and depends a lot exactly when the ice disappeared. It's a very sharp change. And the strand lines for the terrestrial margins of proglacial lakes on the margin of the ice sheet, where They're very sensitive to the drainage sills where that water was actually running out. The height of the lake depends on the sill controlling the outflow, and that, again, that was very sensitive to ice margin position. So those two I don't emulate, but I do score them in the final ensembles. I should speed up a wee bit. Error models, uplift data. Because I've thinned, I just assume a simple Gaussian with no correlations. I just use the stated error bars. Relative sea level, as John T. mentioned, is a real mess. And with Radford, we came up with a split T distribution to allow for long tails. Parameters, some of the parameters of the T distribution are actually inferred from the database via the Markov chain Monte Carlo sampling. And then I also try and allow for some systematic simulator errors. We allow a bit of scaling and time shifting of the relative sea level predictions when comparing them to observations. But there's no explicit taking account of spatial correlations. It's another kind of issue I'm trying to grapple with. The emulators, as I'll get into in a minute, are Bayesian neural networks, so they also give you confidence intervals for their predictions, and that's also used in the error model during the Markov chain sampling. Major errors that I don't have any way of quantifying right now are the inferred margin chronology, especially for North America, as I said, and again, most of the structural error in the model.
Why did you pick you were using the RSL is the
Relative
relative sea level, and this is to do, basically this is the sort of the sea level. This is to do with ground uplift, is that right? When you say RSL, is that?
It's a relative measure, so it's this time data point, time elevation point of where a clamshell was found at present day, but what's the actual date, C14 or OSL date on that? So where was that sea level in the past?
Okay. And you have long tails
Yes.
in this thing, and you use the T distribution because it has long tails?
Yeah.
For any other reason?
No, again, it's a step away from Gaussian, and it's long tails, and it's a split T, so we allow different tails in different directions. So it's two different T's going in both ways.
Okay. All right.
Okay, that was
Okay, yeah.
what we came up with.
There may be easier things than that, but that's.
Yeah, well, maybe we'll sit down with you and Jonty again to come up with a better error model. Calibration. Again, for most of you, I'll go through fairly quickly. Should be mostly understandable. You've got observations. You need some kind of inferential calculator, a way to sample your probability space. So use Markov chain Monte Carlo, use a Bayesian framework. You have your set of calibration parameters, and you have the model, which we can't run on the time scales. So that those question marks get replaced by an emulator. And I won't go quite. There's a few other constraints as well, but I won't go into too much into those other ones. I think I've got enough detail on the data and the constraints. Just want to underline in terms of the emulators, the Bayesian neural networks, which means they're self-regularized. You don't have to, regularization means you're avoiding overfitting, so you're not fitting, you don't end up emulating noise. You're just trying to emulate the actual signal in your training data. And non-Bayesian neural networks usually have to rely on something like splitting of your training sets. You're reducing the actual training set and using some of it as a test set, so you can find out when you start to overtrain your neural networks.
So are you estimating your structural discrepancies each time around that side as well?
The error models, not the structural discrepancies.
Not the structural discrepancies. Are they considered? You fix them beforehand.
Well, I don't really have I'm still figuring out how to quantify structural discrepancies, so.
Fine.
Okay, that's why I keep on asking about it. But anyway, so you don't have to split the training. You can use all the training data without worry about overfitting.
So Lev, just on that point, your simulator is deterministic.
Yes,
So there's no noise.
there's no noise. There is nudging with this margin forcing, but there's no noise in the system.
So is this self-regularization feature necessary in your particular application, or could you do something without it?
Oh, I think it's still, the system's not linear enough that there's actually the relative sea level networks for a while we were using, actually it's really non-Bayesian, where we didn't regularize because there was so much data, they weren't ever really getting fully trained. But then I started splitting the relative sea level neural networks to kind of speed up, so I made regional neural networks. And I ended up overtraining them, which I noticed. So it's still, that can be a problem. So even with deterministic model, you have to watch out for overfitting. The other nice thing is Bayesian neural networks give you confidence intervals for predictions.
So how many climate forcing parameters were there?
The total number of calibration parameters is 29 for Eurasia, 39 for North America right now. Climate forcing was on the order of 20 for precipitation for North America.
So there's 24 parameters that are strictly due to uncertainty in forcing.
Yeah, and climate forcing. Okay, and then this whole process is iterated several times. Okay, so I'm going to go through a bit more in detail. I just want to go through a bit more on the neural network. So, generally using two hidden layers. And I'll go through this quickly for those of you who are not interested in neural networks. But for the most complicated neural network, we created this extra geometry of having kind of a separate subnet for the longitude and latitude. So this is a neural network for relative sea level, which is a function of space, the actual data site location, as well as time, and the simulation parameters. And also found it useful to scale the relative sea level by the time, right? Because in farther back in time, higher the relative sea level. So you can take out some of that simplified, kind of semi-linearize that signal by just dividing it by time. So that's what we actually do the neural network training on, and that's what the prediction neural network is. So I want to say about that. Give you an example then of quality of this. So a couple of days ago, I'm just in the current calibration right now, and just created a 100-member test set. So I generated some new data from a previous Markov chain sampling. Ran the model with that, and then used the old neural networks and compared what the simulator generated to what the neural networks predicted. And this is for the margin forcing, which we deal with the log, actually the margin forcing. And that margin force is actually broken into whether there's missing ice or whether there's too much ice, whether there's ice where there shouldn't be. So it's actually two different metrics, or two different diagnostics. And this is a missing ice component. So this was the worst emulator I had of the previous set. Give you an idea of the scatter.
Did you say that the Bayesian neural networks come with an assessment of the uncertainty?
Yeah, and I checked that too then. So actually the confidence intervals predicted by the neural networks, there were 12,000 data points, and the 10% and 10 to 90% confidence interval covered about 90% of the data points.
Right.
Okay, so the confidence estimates seem to be quite accurate, if maybe a bit pessimistic. Relative sea level, which again, this is a much more complicated process because you've got temporal and geographic dependence in it. But at least for Eurasia, North America is a lot more of a challenge. I can get really nice fits. Okay, so this is on a test set. This was not training data. This is new model runs. So this is the emulator, and this is the simulator. A few other details with the calibration. The priors were specified by, I guess based on my own judgment and from past modeling. Initial priors were, for each calibration parameter was specified by just kind of a univariate quantiles, 0 to 100. And then the final results, because I had so many different metric components, and I'm not able to account for structural error, I actually adjust the final sigma, basically the noise factor, when I'm producing ensemble means and variance statistics, based on kind of personal examination of the model runs and looking at, let's say what the model scores were in the top 10%, whatever, and are those models all half decent? If not, then I make the sigma narrower. If they're all fairly reasonable, then I make the sigma wider. So until I can come up with a complete error model, I'm having to do this part by choice. One other key aspect is that the final results are always based on the full simulator. And so I have to correct that. And there's also, again, some metric components that I'm not able to emulate. So in terms of coming up with the posterior distribution, I won't go, I'm assuming those are interested already know all this stuff. I'm having to scale the likelihood by ratio of likelihoods from the simulator. I divide it by the likelihood function that was actually predicted by the networks. Okay, from the Markov chain sampling. And then I also then a factor for the likelihoods from the other constraints that I'm not emulating. Is this enough? Do people want more details about the calibration process, or has that kind of been enough? I'm not.
Can I ask, when you do your MCMC to calibrate,
Yep.
and you want to know what the simulator will say at a new parameter value, do you draw from the emulator, or do you say that the distribution of the emulator will be this is its likelihood?
I draw from the sampling's done with the emulators, and I draw from that sampling.
So you simulate from the emulator.
The Markov chain sampling is from the emulator, and then I sample from the chains. Once the chains are converged, I sample parameter vectors from those chains, and then run the full ensemble. Maybe I'll go through a bit more detail then. So in general, I'm trying to break up into general calibration approaches. So general slide, right? First, you have to figure out what your calibration parameters are. If you're doing any kind of calibration, non-trivial, especially in this kind of when you have very poorly constrained forcings. You need to come up with a prior distribution for your parameters. That's, again, takes some thought, but it's not, it's enough calculating power, it's not so critical. Have to identify appropriate calibration data and pre-process the data, either thin it or orthogonalize it, whatever. Again, I think that's really important. When you're calibrating, it's so important. It makes more sense to calibrate over high quality data than to have a lot of noisy data. At least that's been my experience. Maybe the statisticians might want to differ. Error models, I've already mentioned, are a big challenge. Then you have to generate initial training ensembles with the full simulator, design your emulators, do some kind of sampling, this whole framework, Markov chain Monte Carlo. And then you have to do this iteratively. Okay, so if you do it once, you come up with kind of a distribution based on the emulators, what's a reasonably high probability set of parameter vectors. You actually run your simulator with those new parameter vectors, you'll find out that there were errors in that, so you've got not as high probability you want. And then when you rerun it, you can use either the cumulative training data or might be some reason to choose certain subsets of it. And then you can basically retrain the emulators on a higher probability set of data. So you can improve the emulators, right? Because initially you just start with Latin hypercube, but now you can start with a training data that has much more high probability data, so the emulator should hopefully better emulate the high probability regions of your probability space.
And by evolving the constraint set, you mean just reducing the range that you're...
Well, initially, again, to explore the whole parameter space, we started off with we only used actually about 5 RSL data points, and then a few other constraints. So just try to get, give more exploration of the whole parameter space, and then the next iteration we added more and more. So kind of slowly zooming in to try to avoid, getting too locked in right away with, maybe emulator was missing something and you actually missed the major mode in another part of the phase space.
So when you go into your second stage, do you then reset prior to as it was right at the beginning?
Okay, that's something else I'll just mention too then.
The area in which you explore.
Yeah, actually I adjust the prior a bit. It's not that much of an adjustment, but I don't have that here. What I do is I basically I resample in terms of, once I've done one iteration, I look at the univariate, even though it's a totally multivariate distribution of what the actual probability space is. I just do univariate sampling of each parameter and just create a new prior based on that. And because I'm ignoring the covariate structure, I think that's, Bayesian point of view, you don't reset your prior to the posterior.
Because you started with a prior you didn't believe that you keep on going back to, that it might because I mean, the complicated part is not reusing the same information to keep on sort of upping your confidence in that information. So,
So I shrink the prior, but just univariately. Okay, so I think I'm not breaking it.
but that means then that you actually have that you identify regions that you can shrink. So if it's a complicated windy shape in parameter space that you restrict, like a cigar.
Well, I'm just doing, let's say my original prior range was like this, for just like max and mins, right?
Yeah.
I just shrink it like that.
Well, that's fine. But supposing your cigar goes right the way across, from the top to the bottom. In other words, yeah.
Like that?
No, I didn't mean like that. I mean, just extend your ellipse so it goes to the top left-hand corner and the bottom right-hand corner. No.
Then I'd shrink it like this. Oh, so
No,
from
your
here?
ellipse. Just
this way here.
Yeah.
Okay, then it wouldn't get shrunk.
Yeah, but on the other hand, that ellipse could actually be very thin.
Yeah, but that,
It could be a very. I mean, this is.
yeah, but when you don't set priors, posteriors to priors though.
Well, I mean, all I'm saying is that in my experience, that as you keep on doing this, I mean, it's good if you can actually shrink them on a parameter by parameter basis. But my experience is that you get very, very reduced parameter spaces.
Yeah, but the point is, I don't have the priors. I have no way of specifying. I can't. I'm not modeling the structure from Gaussian process. So I have no way of specifying it. When I do the second iteration, the sampling will again, will restrict that space. But I have no way of, just based on this confidence interval approach of changing the prior that way. What I am, based on discussions with you, what I have been playing around with is, as I mentioned, this issue of not using the full cumulative set of simulator data for the new training sets, but actually just using, because I use it when I do the log likelihood calculation. It's a series of calculations. First, I use kind of more very easy predict neural networks, like metric components, and I sieve the data, right? So if it doesn't meet one major constraint, for a decent amount of ice volume, then it's given a very low probability, basically rejected, right? So in actual space, then I don't need to train all the subsequent neural networks on the full data set, because I only really need to train on the ones that pass that constraint. I leave a bit of a buffer in case the neural network's a bit off, so actually I can put a bit of an error margin on that, but I'm playing around with that, and there's a trade-off because you're thinning data, but you're also having the neural network not have to predict as much of a phase space response surface.
There are 2 points of escape. One, can you remember what is the definition of splice?
Splice sampling? It's a nice way to do Markov chain Monte Carlo, basically, how to sample from a complex distribution. In one dimension, let's say you have a function like this, right? If you want to sample from that distribution, you can just do uniform sampling, which is easy to do, of the area underneath the curve, okay? 2 dimensions, then you just do uniform sampling of the volume underneath the surface. That's basically what splice sampling is. Sorry, slice sampling, yeah. Slice sampling.
Okay.
Did I write splice?
Yeah.
Okay, yeah.
So the other thing is, where I have is about the separation of time scales. So each run is for the whole deglaciation.
It's for the whole glacial cycle, 120,000
All
years.
the full glacial cycle.
Okay, because the only starting point I have is last interglacial when there was no ice. We know there was basically no ice, so it's easy to start it. Otherwise, it'd have an initial starting point problem. Any other points? So the initial calibration starts off with the hypercube, Latin hypercube. Yeah, I think that's basically it then. Okay. In terms of results, this is a log metric of the fit. This is actually really old. I'm getting even better results now. I just haven't had a chance to plot it. But you can see some initial training data and then the evolution of scores. This is misfit scores, so lower is better. This was for North America, which says has been a lot more of a challenge than Eurasia. Trying to give you a sense that this is non-trivial. With neural networks, with Bayesian neural networks, you can actually calculate the relevance of each input. Yeah, Ian?
Lev, what was the x-axis on the previous plot?
Is just the run number. Okay, so these were the initial training runs. Well, there actually were a lot more in prior. And then these are just subsequent runs with some iterations of calibration.
So are you counting simulator runs? Is that 9,000 simulator runs?
Yeah, well actually, when I originally started this, I only allowed put four digits. It's like, what was it, the year 2000 problem? I originally just put 4 digits in all my scripts, right? I'm on my third run through 10,000 now, so this was the very original.
But that's the number of simulators.
That's the number of simulator runs.
Yeah.
Okay, it's always the final results are always based on the simulator runs. Give you a sense of complexity of the response surface. Again, it's just that there's no simple, linear responses. This is one of the high relevance variables in Bayesian neural networks. You can look at the hyperparameters controlling the weight distributions of the inputs, and from that you can tell, which of the inputs are more critical or have a stronger effect on the final prediction. And this is the scaling factor for the overall precipitation. It's one of the most important inputs. And this is a total RSL, relative sea level score, okay, based on model runs. Okay, so this parameter range, relative sea level score, even though it's it's one of the most predictive, one of the most critical inputs, you can see there's no simple structure, right, in the response. Here's one lesson. If you try to overload a neural network, so originally we were trying to train a neural network, one neural network, our relative sea level neural network for all 8,858 data points in the database. And this is a prediction versus the actual simulated result. So emulator versus prediction. You can see when we were doing that, it was no predictive value. When we shrunk it down to 280 data points on one neural network, we got much more. And again, this is old. I'm doing better now. Just haven't had a chance to plot it. For Eurasia, a lot better, as you saw with those neural networks for Eurasia. North America is just much more complicated response. Time-wise, I'm pretty well out of time, so I'll just give you a sense of what you can create in terms of snapshots in the past. You can see the velocity fields, which are of interest to glacial geologists. Compare it to observations. Once you have these probability distributions, you can compare features. For instance, I can compare ice thickness versus rate of misfit to uplift of a critical uplift data point, and see how that changes for different slices of the probability distribution. Give you an idea of the phase space. What I've done is taken 3 different, just ad hoc, I guess fairly half-decent model runs. Okay, fixed all the parameters except one, which was fast flow control parameter, and then I just created, I think about a 10,000 parameter set, just going over the whole range of that fast flow parameter, and then ran it through the neural networks. So you can see for 3 different parameter vectors, just changing one vector, totally different response surfaces. Give you a sense of complex behavior of at least what the neural networks are predicting. Generate error bars for different things. Final things that might be of interest to people here is the applicability of the methodology. Okay, so this was in some ways a state space estimation problem, right? In a crude sense, because I'm trying to figure out what was a deglacial state space. But in other ways, it's just a parameter estimation problem. Calibrations are using 1,000-member ensembles, 39 parameters, 2 to 4 iterations. 2 for Eurasia seems to work fine. North America, I need at least 4. Again, there's more parameters, more complex response. I had a grad student who I had to show a poster up, I guess, at the workshop 2 weeks ago. We tried using the same approach for calibrating the planet general circulation models, the fast GCM we used with the mixed layer setup. calibrated 6 parameters, did 2 ensembles. I told them restrict it to 100 members. Again, we weren't trying to optimize the number of simulations. This is easy to do. 100 members, I think, is within regime, at least for fast GCMs. It's defensible. Okay, so anyway, was able to get quite good results. So these numbers, you maybe can get by with less numbers. We haven't tried to optimize that. That's not worth the time for us to play around. In terms of time cost, the sampling, most expensive neural network to train is a relative sea level neural network, and takes about a week to get it, I think, fully converged. Markup chain sampling, after a day or two, I can already start extracting parameter simulator runs and starting to run the simulator. And I was thinking for Neil yesterday, we were talking about some of the stuff they're working on, when he's talking about having the challenges of nudging, how to do state space estimation when you have nudging, and basically have a nudging component in this model, and I'm still able to do the estimation. Really running out of time. Key lessons: assemble as much calibration data as possible, and then intelligently thin it. It's really, quality is much more important than quality and than quantity. Work closely with the data people, because there's a lot of hidden errors which they don't usually quantify, and even just their error model is usually a lot more complex than just a plus or minus they give you in their published papers. Start with as many parameters as you can, and then you can do data thinning based on, use neural networks on the automatic relevance determination methods. One of the longest, I've been doing this for about 5 years, more than 5 years now actually. I contacted Jonty with this problem, I think 2003. Is that I keep on, and I go so far, I get new data, or I find I just kind of hit a wall in terms of the fits I can get, so then I have to add more parameters, and then basically restart the whole calibration process. And in that sense, it's really important to plot the results of your calibration, because one thing I've noticed is that if your model basically doesn't have enough degrees of freedom to cover the target space, the MCMC method seems to have a way of finding some ways of making the model fit. I was getting holes in, it was basically able to come up with some set of EOFs from the inner model variants to create holes in the ice to fit some RSL data. So it's really worthwhile to plot your data, see what's going on. This is why I'm here. So at least one of the reasons I'm here is trying to get answers to some of these challenges. I've already gone through some of this. But how to quantify structural error, so that I don't have to basically do really come up with meaningful error bars. Right now I can only give error bars that take into account model misfits and data uncertainties. I don't have a way to quantify the structural errors in the system. So all my error bars for final results are always limited. They're not complete. In terms of how to improve calibration, it's worthwhile having a lot of Markov chains. Given the price of computer clusters now, I've got I guess 500 cores to myself or to my group now. It's easy to do a lot of chains at once. So it's a way to avoid multimodal limitations. Is just start off like 100 chains, and we also play around with using different constraints set to the different chains. So I have some chains that have a much more constrained likelihood function, and some that have a broader likelihood function, as a way to kind of speed up the calibration process and make sure you're not getting hooked into too small, a single mode in the probability space. And a couple questions I've had too. This basically ends it. Is there any point to using different emulators for the Markov chain sampling as opposed to the final scoring of the ensembles? And I'm just wondering, because the error models can affect in terms of how the Markov chain sampling goes, and I wonder if there's ways of somehow using the error models to improve the sampling. I don't know, just some ideas I've had. And another thing I've noticed is when you do this with the Markov chain sampling, some of the chains seem to do a lot better than the others. So if I start the Markov chain sampling, after 2 days I can extract some parameter vectors from it, run the simulator, but keep the Markov chains going, and then I can find some chains that produce some much better fitting simulator results. Is it worthwhile just concentrating doing the secondary sampling from those chains?
When you say better fits, you mean better fits to the observed data?
Yeah, better log likelihoods.
You mean that point-wise or as a whole vector of space?
Well, the parameter, in terms of the actual, some chains, when I take the sample from those chains, use those parameter vectors and run them through the full simulator, their fits to their likelihoods are better than other chains, right? So I guess maybe those chains somehow, and it started off on the right, because each chain started off in a different point, so they might have started off in a place to capture some local mode. Anyway, it was more than I should have taken. That's it. Yep.
So I work with some land ice modelers, and we seem to spend a lot of time talking about basal sliding parameters. I didn't see that explicitly called out. Is that in
That was that fast flow parameter. It was basically the viscosity of the subglacial till. So the model takes into account, uses till maps and also surface geology. Actually, it's even more than just till thickness, but estimates of surface roughness. And then also have another calibration parameter is a sliding parameter as well. It's controlling, so sliding over bedrock. One thing I don't have yet is basal hydrology, but I was a student working on that. So again, there's always more feedbacks in the system. End up just being more parameters.
So you were nudging the model and then using the amount that you needed to nudge the model as part of your
Cost function.
Yeah.
So I want to minimize the amount of nudging.
But at the same time, you were also having nudged the model, you were using the difference between the model and the observations as part of the error model. Is that right? So you were both using the amount you needed to nudge the model and the difference between the model and the data after you've nudged it in order to determine which simulations, how to weight the simulations. Is that right?
Not quite. I'll try to explain more because I'm not quite sure. I used, in terms of, if the ice margin is not close to the inferred margins, then everything else is going to be totally out to lunch in terms of the impact relative to sea level. So it's nudged towards the margins, but then I have metrics calculating how much nudging was done, basically how many grid cells were nudged at each time slice, and then that's one of the metrics in log likelihood. So the more nudging, the more penalized that model was, or that parameter vector is.
That I think I understand, but I was trying to work out if having done, you were nudging it towards the data, but not to exactly match the data.
Yeah.
And am I right in thinking that you then still do a comparison between the model and the data?
No, not in terms of margin position. The only thing I do is just how much nudging was required in terms of margin position. I have the other data like relative sea level data, and that's going to depend on margins as well. But there's no metric measuring how close it was to the margins. All it just measures. The only metric is how much nudging was done.
And is it given that your original uncertainty was in margin position and what you're then quantifying is a rate of change of margin position that you have to put in the model? Is it easy to map your original uncertainty onto the?
Oh, I think I get what you're talking about. In terms of the uncertainty of the margin position, are you talking about the data now?
Yeah.
What I have is a buffer region. So let's say, the actual margin is here, and I have different error bars. Again, I was defining those error bars for the chronology. But if this is a region, then if the ice is within this region, there's no nudging. Okay.
Yeah. Sure. Yeah.
So it's only if it's outside of that region that there's nudging occurring. So that's basically the error bars in terms of the data for the nudging process. Does that answer your question now?
Sort of, but yeah.
We can talk more afterwards, I guess. Yep, Richard.
So, all the algorithms you've been doing are types of ABC algorithm, approximate Bayesian computation algorithm. So I know they've been discovered many times. Right? So you might be interested to know, because you've done this iterative thing where you did a calibration and then narrowed your parameter set down, done another calibration. So that's a type of sequential approximate Bayesian computation algorithm. So if you're worried about double counting your data, Christian Robert and Mark Beaumont's people have figured out a way to rebalance your particles when you do the next set of your second sweep of calibration, so that you're not double counting anyway.
Where am I double counting?
Well, I wasn't quite clear what you've done, but you took your prior, did your calibration, and then you took that posterior and set that back as your prior in some way.
Well, yeah, but that's what I was emphasizing. Because I'm, 39 or 29 dimensional space, right? And I'm just doing a univariate reduction in the ranges. I'm not really setting, it's a small, it ends up being a small change.
Okay.
I'm not actually setting the posterior to the prior.
Okay.
And I don't have any way, the only way I can, get that structure is from the actual likelihood sampling, the Markov chain sampling.
And there are ways of doing this. I mean, for
Oh,
example,
I'm saying there are ways of doing
if you
this.
cut out the part which effectively a posteriori has 0 probability,
Yeah.
then you could then run it again, just stripping that out, and then just recalibrating your prior over the new space, and you would get effectively the same answer.
Yes.
And that's, I think, all the rebalancing.
But then the problem is how do I actually, I need then some kind of distribution for that covariate space. And the only way I can sample from that space is from the Markov chain sampling.
Well, or through your emulator. You can, by your emulator, you can identify the space.
But only through the log likelihood function.
Well,
I can
guess
sample,
this is-
right?
This is the difference between calibration and history matching, I think.
So,
But anyway, that's
another point along the ABC lines is that because because you're sampling from your emulator, if you didn't do that, so when you do your MCMC, okay, you sample from your emulator each time. So this may, certainly in the Metropolis Hastings setting anyway, I know you're not doing Metropolis Hastings, but in the Metropolis Hastings setting, this would mean that your variance of your Metropolis Hastings ratio would be higher. Whereas if you just use the likelihood of your emulator instead, rather than simulating from it, you'd get a lower variance for your Metropolis Hastings ratio, and hence more efficient sampler. Well, I suspect this carries through to the slice sample, but I don't know for sure. But there's a difference between simulating from your emulator and using the emulator likelihood. So in a Gaussian process emulator, your distribution of your emulator output is multivariate Gaussian, and presumably in the Bayesian neural network, it's a similar distribution for your emulated output. So what would
the emulator gives me the mean and then gives me confidence intervals. That's all it does.
It doesn't give you a likelihood function.
Well, the emulator is just predicting, like, let's say, relative sea level, and then I have to define a likelihood function.
So the emulator is predicting your simulator, and you said that it does it in a probabilistic way. So for any input, your emulator gives you a distribution for your simulator output.
Well, it just gives me basically all I'm taking is I don't think that's probably all I can generate with that code is the mean and 10%, 90% confidence intervals.
Okay. That differs from a Gaussian process. We get a distribution on a likelihood.
Yeah, no, this is not Gaussian process. This is just.
Okay.
So obviously the question, sort of the biggest question in the whole thing is this question of structural error.
Yeah.
Now, obviously the ideal gold-plated way of doing this is by very clever methods to actually establish a structural error. Now, there is a sub-question you can ask, which is how tolerant is your method to structural error? Okay, in the sense that at the moment you have built no structural error in. Yeah? Okay, so obviously in some sense you're overfitting. I mean, you're in a sense, you're getting, by writing down a model in which sort of the model basically gives you the observations plus gives you the reality. Reality is then observed with error. Yeah. Then you're expecting. I mean, the whole model predicts a closer fit than you would actually expect if you built the full structural error modeling in as well. Yeah.
Yeah. Well, that's why in the end I have to basically hand tune the final noise factor.
Yeah. But so the notion of hand tuning, of course, is an interesting question all by itself. Yeah. Okay. And it seems to me that well, there are ways of actually building, doing it through the modelling process of understanding effectively how sensitive your whole method is to structural error. For example, I don't know whether you've ever done this. I mean, one of the ways, because there are two issues: is your method working? Because things get quite technically complicated. I mean, is the method working if the data was generated the way you're describing? Yeah. Okay. And then how much mismatch between the way the description that you're given and how the data is actually generated can your method tolerate? Yeah. So the way I would normally do this is that you start off by constructing, if like, a synthetic example where I do generate my data effectively from my model, okay, and at that point, so calculations on that are showing me that my method works, assuming that the model is appropriate. So it sort of goes through all the technical questions. Have I tweaked it wrong? Am I overconfident, underconfident? Just at the basic.
Yeah, we'll just add like
And then
model
at
plus noise.
And at
but
that
yeah.
point, you can then start introducing different forms of structural error into the data that you generate, and then go back to your model, and then you can actually see what actually happens to your estimates as you have this unaccounted for structural error.
Yeah, but how do you?
Well, this is the point. I mean,
Here's
so obviously, as I said, the gold-plated way is
Yeah.
to work out structural error just perfectly, and then you just build it in, and then it's already in the model. But failing that, you actually do explorations. You can think of sort of forms which you haven't actually settled on yet, because that requires sort of the deep system sort of side. Where you say, well, these are the kind of structural errors that I could currently envisage that I might come to. Build them into your synthetic example, and then see what happens to your estimates, and see, and you start getting a feel for whether your method just falls over, whether effectively you can hand tune it, roughly how, like say, a 10% error correlated across observations, because it's a correlation structure across outputs, which I think is the one that really kills you, okay? Which is, I think, very hard to hand tune against. So you start to get some feeling for, firstly, whether you can hand tune it, and effectively how much structural error that you haven't accounted for you can tolerate and still get meaningful results. I find that quite a useful method.
Yeah, the challenge is even come up with how to, conceptually come up with like meaningful structural errors to put into that.
Well, for example, I mean, for the climate forcing, which you want what's the largest one,
Yeah.
okay, then you've parameterized it.
Well, some,
Yeah.
it's
See, I can easily imagine how I do it with the kind of emulators I'm used to constructing, but when you tell me you're using Bayesian neural nets, that kind of is, I'm out of my comfort zone. Yeah. But I can see, for example, if you tell me that climate forcing is the biggest issue, okay, then I would think about, you to a certain extent have parameterized climate forcing, but I could now imagine generate sort of possible climate forcings consistent with those parameterizations. I could then imagine creating basically an exchangeable class of models given those realizations. I could imagine now fitting a class of an exchangeable set of emulators, and I could now imagine quantifying the uncertainty that I've overlooked by not taking into account the fact that I have an exchangeable class of emulators and what my representation should be. So I can see a way through that. But the point is, without necessarily strongly being committed to saying that in the end, when I write my scientific paper, I'm going to say that's what it is. But I can start getting a feeling for the kind of errors that don't seem absurd to me, and how, I mean, if I decide that my method is fairly robust, I can build quite a lot of error in, and that it has to be really quite large to beat all the observational uncertainties, and basically I'm recreating, then I'm less worried. As soon if I find, and because a lot of these Bayesian things, in my experience, I mean, because they are likelihood based, and the likelihood a likelihood method just wastes the height of the likelihood and the height of the prior at different points. And that's very point sensitive. If you find that building a bit of correlation into your structural discrepancy really moves the solution a lot, then you're aware that that's a very important thing to focus on. So I think there are a whole bunch of experiments you can actually do to, in a sense, to identify the kind of discrepancies which you need to think very carefully about. And you start quantifying the magnitude of the effects which will actually influence your answers. And you can do that even before you decide what your actual structural discrepancy should be.
Okay, I'll sit down with you, just think that, how to do that in detail, and use a kind of algorithm for that. But
My question was, I think it's actually the first sentence of what Michael has said, which is, have you done identical twin tests to test that your problem is tractable in the case of the perfect model?
we did it with the planet simulator for the GCM. I haven't done it with this one.
And it does work
For the planet simulator, yeah.
Off your time.
Yeah.
Thank you.
Long.